So I'm going to have you read 1-7 again tonight. We'll have a 1-7 reading quiz. I don't have my headset on. Okay, so we're just going to do a little brief intro to 1-7 here. You're going to read it again tonight, and we'll have a quiz on it next class. Okay, so one common feature in many mathematical models, when we try to build a model that models a real-world situation, is the presence of a parameter along with the other variables involved. So remember, a parameter is something that doesn't change over time. They're quantities that don't depend on time, but assume different values depending on the specifics of the application, right? So for example, the Malthusian model of population growth, dp dt equals kp. That model contains a parameter k that's different for different populations, like a human population versus a rabbit population are going to have really different values of k, right? Same thing with Newton's law of cooling. It's got a parameter k in it, and that k depends on what container is holding your thing that's cooling, right? If you have like a thermal mug versus a paper cup, the k value is different. So our goal in 1-7 is to study how the solutions to a differential equation change as the parameter varies. Okay, so there's many differential equations encapsulated in there with a different parameter, and we want to know what do the solutions look like as you change the parameter. Okay, this is often a really important question to answer when you're doing modeling in the real world. All right, so we have a family of differential equations given by dy dt equals y squared minus 4y plus mu. This is an autonomous differential equation, depends only on y. Mu is just a constant. Okay? It's a parameter that can change based on what we're modeling, but it's just a number. Okay? So our goal is to see what do the solutions to these differential equations look like and how do they depend on mu, right? Do the solutions look drastically different for different values of mu? Yeah. So we begin by investigating the parabolas defined by the right-hand side of the differential equation. So we're going to call them f sub mu. They look like y squared minus 4y plus mu. So we know how to graph parabolas. You can just put it in your graphing calculator or complete the square and put it in that vertex form. And then I'm going to study them for various mu's. Just going to look at these different parabolas with different values of mu. So f sub 0 means make mu 0, and this is just going to be y squared minus 4y. Yeah, we're making mu 0. Yeah, so f sub mu is representing a whole family of functions, right? The inputs are y, but each different mu gives you a different function. Yeah, kind of is like 2 inputs. Yeah. All right, so I graphed this for you. F of y equals y squared minus 4y. I'm going to label the axes appropriately here. What is my horizontal axis? Y. Yes. That's my independent variable is y in this case. F, I guess. F of y. Which also is dy dt. Actually, that might be better to keep in mind that this is a graph of a derivative. Dy dt. That is the right-hand side. Y squared minus 4y represents the right-hand side of my differential equation. Right? So it's a derivative. All right, so I can use this parabola to draw a phase line corresponding to dy dt equals y squared minus 4y, which is f sub 0. Okay, so I'm just going to put a vertical line. Where are my equilibrium points? 0 and 4, right? Places where the derivative, which is what I've graphed here, where the derivative equals 0, happens at 0 and at 4. And again, this is a graph of the derivative. So when I'm smaller than 0, right, to the left of 0, is the derivative positive or negative? Positive. It's above the x-axis. You're thinking tangent lines again. This is already the graph of the derivative. So if I want to know if the derivative is positive or negative, just look at whether it's above or below the x-axis. This is above the x-axis, so I put in an up arrow. Okay. Between 0 and 4, the graph of the derivative is negative, so I put in a down arrow. And then after 4, I have positive up arrow. So that's a phase line corresponding to mu equals 0. I could draw different phase lines, a different parabola and a different phase line for every possible mu, right? So there's infinite parabolas and infinite phase lines that I can draw when I just pick random values of mu. So I've just picked one random value, I sketched what it looked like, and that helps me draw a phase line. Okay, so for different values of mu, if I pick something other than 0, how would it relate to the graph I just drew? It would shift the graph vertically up or down by mu, right? Yep. Shifts F0 vertically by mu. All right, so I want to find the important mu's. There are mu's that make where all of a sudden the graph is qualitatively really different, right? So if I graphed f sub 1, right? F sub 1 would mean make mu 1. It would shift everything up 1, right? So f sub 1 would look kind of like that goes there, that goes up 1 there, something like that, right? Nothing insane, right? Not really any different. It still has 2 equilibrium points. It's still going to go positive, negative, positive. So the phase line is going to look almost identical. It's just going to change where those, that's not going to be at 0 and at 4. It's going to be at like, I don't know, point something and 3 point something. Yeah. Oh, you're right. Thank you. If I shift up by 4, I'm going to have a very different phase line because I'm all of a sudden going to have only one equilibrium point. All right, so that is what we call a bifurcation value. When all of a sudden the phase line looks completely different than it did before. So finding a bifurcation value, here I have on the same axis graph the parabola that has its vertex tangent to the horizontal axis. So that would be right here. If I shift everything up 2. 4. Shift everything up 4. I got to read the scale of my graphs here. Okay. Shift everything up 4. And if I draw a phase line, now the phase line is going to look really different, right? There's only going to be one equilibrium point on it, and the arrows are going to point up on either side because it's always positive. Yeah, so it will be a node. So really quick, phase line, it only has one equilibrium point at 2. And it points up and up. That's for mu equals 4. If mu equals 5, there's going to be no equilibrium points, right? There's no more equilibrium points because it never touches the x-axis. So you're going to have a phase line that looks something like, for mu equals 5, just an arrow because there's no equilibrium points, but everything's always positive. So what value of mu gives you that parabola? You already told me that was mu equals 4. In this case, it was pretty obvious. You could just look at the graph and use your knowledge of vertical shifting to figure out what mu was important. But if it's not quite so obvious, finding a bifurcation value, which we call B, it's where the interesting things happen. And the way you typically find it is, yes, 1, you need f and f prime to both equal 0. Set f prime of mu of y equal to 0. Solve for y. Solve for y. Okay, so what I did there was my parabola was y squared minus 4y plus mu. So take the derivative and I get 2y is it plus 4y? Just double check here. Minus 4y. So minus 4 equals 0. Solve for y and you get 2. And then step 2 is set the original f mu, not its derivative, but just f mu equal to 0. Plugging in y value from 1 from step 1, solve for mu. I know. So my original f sub mu is y squared minus 4y plus mu. Set it equal to 0, right? Plug in the y value you solve for in part 1, which is a 2. So I have 4 minus 8 plus mu equals 0. You solve for mu and you get 4. So we were able to really clearly see that based on our college algebra knowledge of functions. Sometimes it won't be so clear, and this is kind of a step-by-step procedural way of finding your bifurcation value. This is the bifurcation value. All right, so the idea is for every different mu, we have a different phase line, right? But there are some really particularly important phase lines, and they happen at the bifurcation values. They're important because they mark a distinction where something qualitatively different happens. All right, so choose two nice numbers, one a little bit bigger than b and one a little bit smaller than b being 4, the important mu we found. 5 and 3, I like those. 5 and 3. So on the same axes where we've been drawing parabolas, we can draw these two new parabolas, different members of the family. Okay, so I'll do, so 3 is going to be, I'm going to shift up 3 so it looks something like this. So that's f sub 3. This original blue one was f0, and the pink one's the bifurcation value, f4. And then I'll do one more, which was f5. So each of those parabolas could get its own phase line. And in fact, I've already sketched a couple of them. I've got 4 and I've got 5 down here. So a bifurcation diagram is what you get when you take all the different phase lines and put them in a chart, like line them up next to each other. Okay. So this, my horizontal axis is mu this time. So I want to know, I'm going to look at the phase lines lined up next to each other as functions of mu. So what happens to the phase line as we change mu? So I know the vertical axis is just a phase line. These are phase lines, yeah. So this is a phase line here. This is a phase line that corresponds to mu equals 0. I know what that looks like because I drew it right here. That's the phase line for mu equals 0. Got equilibrium points at 0 and 4, and it goes up, down, up. So I put an equilibrium point at 0, put an equilibrium point at 4, and it goes up, down, up. Yeah, so at 4, that was my bifurcation value. I'll do 4 in a new color here. So at 4, I had 1 equilibrium point. Where was it? 2. And it was up, 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 up. Not always. In this case, this is a node and it's a bifurcation value. Yep. It's a common thing that can happen. Yeah. So after this, there are none, right? All of these phase lines afterwards have no equilibrium points, and they're always positive, right? All of the equilibrium points before the bifurcation value have all of the phase lines before the bifurcation value have two equilibrium points, and they go up, down, up. It's just the location of the equilibrium points that changes. So we did 3, right? We graphed the one at 3. And I don't know exactly where the bifurcations are. I mean, where the equilibrium points are. I think it was at like point something and 3 point something. Just being pretty eyeballing it here. That's exactly what it does. Yeah. So the bifurcation diagram, and then afterwards, right? Afterwards, the equilibrium points just keep getting further and further apart. Again, I'm just eyeballing these, right? And you can connect all your equilibrium points, and you get a diagram. This is called a bifurcation diagram. It's just a bunch of phase lines next to each other, lined up horizontally, where you draw the phase lines based on mu, the different parameter values. That's a coincidence. Yeah. You can get some pretty crazy looking bifurcation diagrams. All right, I think that's enough for today.